So far, we've been looking at hypothesis tests for means and for population proportions, but we can also consider a hypothesis test for variance. So you'll recall that if y1 through yn are independent, normally distributed random variables with mean mu and standard deviation sigma, then n minus 1 times the sample standard deviation squared divided by the actual standard deviation squared has a chi-square distribution with degrees of freedom n minus 1. And that will be the basis for our hypothesis test for variance. So we want to consider testing the variance against, say, a hypothesized or a published value. So the question we're looking at is our null hypothesis true? Sigma squared is equal to some hypothesized value, sigma sub 0 squared, or is there significant evidence for the alternative hypothesis? Sigma squared is not equal to sigma sub 0 squared. And that, of course, is a two-sided alternative. We could consider some one-sided alternatives where sigma squared is less than sigma sub 0 squared, or where sigma squared is greater than sigma sub 0 squared. Our test statistic is going to be n minus 1 times the sample variance divided by our hypothesized variance. And that, of course, has a chi-square distribution with degrees of freedom n minus 1. So we'll want to consider some rejection regions that correspond to our alternative hypotheses. For the two-sided alternative, we can consider a rejection region where our chi-squared statistic is either greater than chi sub alpha over 2 squared. So our test statistic could fall in this region, which has area or probability alpha over 2, or our test statistic could be less than chi squared 1 minus alpha over 2. So it could fall into this region, which has an area or probability alpha over 2. For our one-sided alternatives, say when sigma squared is less than sigma sub 0 squared, we could consider a rejection region where our chi-squared statistic is less than chi squared 1 minus alpha over 2. So it falls into this region, 1 minus alpha. So it falls into this region, which has an area of alpha. Or for the alternative where sigma squared is bigger than sigma naught squared, we can consider a rejection region where chi squared is bigger than chi sub alpha squared, so that it lands in the upper tail and the area for that upper tail is, again, alpha. So that gives us the three different possible rejection regions depending on our alternative hypothesis. So let's proceed to an example. So for example, standardized tests like the ACT should produce scores with a large amount of variation distinguished between students. Historically, the standard deviation for the ACT has been 5. Suppose that 20 students take a new version of the ACT and sample standard deviation is 6. Our scores from the new test significantly more or less variable than scores from the old test, and we will use a 5% significance level for this test. So we want to consider a null hypothesis that sigma squared is equal to 25, which is the variance from the previous test, or an alternative where sigma squared is more or less variable than 25. So we're considering a two-sided alternative here because we have no reason to believe that the new version of the test should be more or less variable than the old version. We're going to look at the chi-squared statistic. That chi-squared statistic is, again, n minus 1 times sample variance over the variance sigma sub 0 squared. We have 20 students, so n minus 1 in this case is 19. We have a sample standard deviation, which is 6. So s squared is 36. And then we have the standard deviation we were comparing to, which is 5. So that is a sample or a variance of 25. And if we make that calculation, our test statistic is 27.36. And since we have 20 students, the degrees of freedom is 19. And now we need to figure out a p-value. So what I'm going to do is I'm going to try to figure out a value of p over 2. I'm going to try to figure out what the values for the chi-square are where that surround p over 2. So I'm going to go to the chi-square distribution chart, and I'm going to move down to the upper tail, and for a significance level for degrees of freedom of 19, I'm going to look at this row. And I'm going to try to locate our chi-squared statistic. Our chi-squared statistic was 27.36, and I'll notice that 27.36 lands between this column and this column. And it gives us a sense of where p over 2 is. So if we kind of go back here, we go back here, then we see that p over 2 was between 0.05 and 0.1 because it was between the columns for 0.05 and 0.1. And so that tells us our p-value is between 0.1 and 0.2. Now, we wanted to compare our chi-square statistic to, say, chi-squared 1 minus 0.025 for 19 degrees of freedom, and chi-squared 0.025 for 19 degrees of freedom. So that's what we're comparing our chi-squared statistic to. So let me see if I can locate those two values, okay? So for 19 degrees of freedom, we can start with the chi-square for 0.975. So I'm going to look for the chi-square for 0.975. 19 degrees of freedom, that's going to give us 8.9. And then when I'm looking for the chi-squared for 0.025, I can see that the 19 degrees of freedom gives me 32.85. Okay, so let me see if I can record those two values for a second. Okay, so for the chi-squared for 0.975, 19 degrees of freedom, we had 8.91. Okay, and for chi-squared 0.025 with 19 degrees of freedom, we had 32.85. And hopefully you can see that our chi-square statistic is not in the rejection region. It is in fact in between these two values. So it's in between the chi-squared for 0.975 and the chi-squared for 0.025. So it's not in the rejection region. That corresponds with the fact that the p-value was bigger than 0.05. It happened to be between point 1 and point 2. And because of that, we fail to reject the null hypothesis. So either one of those criteria can be used to fail to reject the null hypothesis. So in this case, there's not enough evidence to say that the new test is significantly more or less variable than the old test.